Hello everyone. Before we get into further understanding about what impurity functions are and what are the different impurity functions that we can leverage in order to determine what could be the right feature split for the decision tree model that we are going to create. So we have evaluated all possible independent variables to have feature splits which could help us divide our data into subgroups or subnodes. So I have listed down all the key takeaways from our previous couple of sessions. So these were the three different variables that we have evaluated, one of which is credit rating, the other one is credit score, or the other one is credit card and income group. So we have evaluated all of these features for splitting this particular data or partitioning the data into subnodes or subgroups. So select the feature split or decision which resulted in as homogeneous subnodes as possible. So ultimately we are going to choose one such feature split which is going to produce as homogeneous subnodes as possible. From the previous exercise that we have conducted, we understood that credit card did not provide homogeneous subnodes. So it provided non-homogeneous subnodes for whatever subgroups that we have tried to assess. We straight away rejected that this could be an improbable feature split here. So we were pretty much confused on what could be the right feature split in between credit rating and income. As a third point, we are going to use a feature or use a feature split that is going to result in as pure subnodes as possible. And the impurity in its subnodes is being measured by something called impurity functions. We are going to discuss about Gini impurity as well as entropy, which are two most commonly used impurity measures, which is going to help us understand what could be the right feature split here. The example data that we have been considering so far, is it credit rating feature split that we have evaluated or income group feature split that we have evaluated could be the right feature split. So we are essentially going to calculate what we call as weighted Gini impurity for the given feature split, so as to understand if that's the right feature split or not. Okay. So to begin with, let's understand what Gini impurity is. Gini impurity, as we know, is an impurity function that helps us determine how well of a feature split that we have implemented. So this is given by this particular formula, which is summation of small k is equal to 1 to capital K. Capital K here is going to be the number of classes. The number of classes in our example data here is 2. So there were positive classes as well as negative class. I'm indicating positive class with 1, indicating negative class with 2. So summation of k is equal to 1 to capital K, p sub k multiplied by 1 minus p sub k. When I try to expand this for the example data, it will turn out to be p sub 1 multiplied by 1 minus p sub 1 plus p sub 2 multiplied by 1 minus p sub 2. Where p1 here is going to be the probability that a randomly chosen data point is going to belong to class 1. Now let's consider an example and try and understand more about it. Let's say that this is my subnode S1. This is my subnode S1 where I observe 3 different data points with positive labels and 3 different data points with negative labels. In total, there are 6 different data points available within this subnode. So we clearly understand that the probability that a randomly selected data point belong to class label 1 or positive class is going to be 0.5, which is nothing but 3 by 6. So P sub 2, the probability that a randomly chosen data point among these 6 data points that could belong to negative point is given by 0.5 again, because there are 3 negatives out of total 6 data points, which turns out to be 0.5 again. So when I try to plug in these values of P sub 1 and P sub 2 in this particular formula, it will result in 0.5 multiplied by 0.5. So 1 minus 0.5 will result in 0.5 again. Again, P sub 2 is 0.5 again, multiplied by 1 minus 0.5, which is going to be 0.5 again. So it's going to be 0.25 plus 0.25, which is 0.5 again. So we can intuitively understand that this subnode S1 is a non-homogeneous subnode. This is an impure node. We cannot clearly make out any query point that follows this particular path where it leads to S1. We cannot clearly make out whether that belongs to positive or negative class because they are proportionately equal within this particular subnode. And hence the Gini impurity that we have calculated at subnode S1 also turns out to be 0.5, which is the maximal possible value as per the curve that we are currently observing here. So G of S is nothing but the Gini impurity. So we are looking at this particular point on x-axis, which is nothing but the probability that it belongs to class small k. So this is going to be a maximum value. This is going to be a maximum Gini impurity value, specifically when your probability is going to be 0.5, specifically when your proportion is exactly half. So we clearly understand that the Gini impurity that we have calculated for subnode S1 is going to be maximal, and the maximum possible value for Gini impurity at any given subnode is going to be 0.50. Let's consider another example. Let's consider a pure node this time. All the data points are positive data points. None of them are negative points. So this is my subnode S2. So clearly P sub 1 is going to be 1. P sub 2 is going to be 0 because 0 out of all the data points belong to negative class. With the expansion, it's going to be P sub 1 minus 1 minus P sub 1. P sub 1 multiplied by 1 minus P sub 1 plus P sub 2 multiplied by 1 minus P sub 2. Plug in these values of P sub 1 and P sub 2. This is going to result in 1 multiplied by 1 minus 1 plus 0 multiplied by 1 minus 0. This is going to turn out to have a value of 0. The impurity here in this particular case is going to be 0. So impurity should be very low, as minimal as possible, in order to attain the goal of decision tree. So the goal of the decision tree model here is going to be to attain as pure homogeneous or as pure subnodes as possible with a right feature split there. So we need to determine the feature split based upon the homogeneity that's reduced in its subnodes. So here your subnode S2 is a pure node or homogeneous node, and hence the impurity that we have calculated is 0. When impurity is 0, that indicates that the data available at subnode is pure or homogeneous. I believe you have understood the difference between impurity and purity that I'm clearly talking about with the help of the numbers that we have arrived at. Okay. So with this as a context, we clearly have understood that the maximal possible Gini impurity value could be 0.5. And this actually is at a specific probability value that we have identified to be 0.5 again. Okay. So what are the steps to calculate Gini impurity for a feature split? So far, we only have calculated Gini impurity at a given subnode. We have calculated Gini impurity at subnode S1, which turned out to be 0.5. And we also have calculated Gini impurity at subnode S2, which turned out to be 0 because it was a pure and homogeneous node. Now let us look at calculating the overall Gini impurity for a particular feature split. So these are the two different steps that I have mentioned. These are the steps that are to be followed in order to arrive at the overall Gini impurity for a feature split. I'm not going through these steps here, but rather I'm just going to get into the mathematics behind it so as to understand how we can calculate the overall Gini impurity pertinent to a specific feature split here. Let me consider this example where we are splitting this particular data based upon credit card. So we clearly have understood earlier that the subnodes S1 and S2 that we deduce based upon this particular splitting criteria on credit card resulted in non-homogeneous subnodes where 50% of them belong to defaults and 50% of them belong to non-defaults in both the subnodes. So this is as good as not having this split condition at all, because that's what we observe at root node itself. This is what the understanding that we have gained so far. Now let us look at calculating the Gini impurity at subnode S1 as well as subnode S2. And once we calculate the Gini impurity at subnode S1 and Gini impurity at subnode S2, we will also calculate the overall Gini impurity. The overall Gini impurity by taking into account the weights of both these subnodes. What could be the weights of both these subnodes? So we observed 12 different data points that are present in subnode S1 out of total 16 present in population. It is in the root node. So this is a weight associated with subnode S1. What could be the weight associated with subnode S2? There are only 4 points out of 16 in total. So this is a weight that we can associate with subnode S2. And we clearly also have understood that the Gini impurity that we can calculate at subnode S1 will result in a value of 0.5. And Gini impurity when you calculate for subnode S2 also will result in a value of 0.5. Let us calculate for one of these. So let me expand the formula, like P sub 1 multiplied by 1 minus P sub 1 plus P sub 2 multiplied by 1 minus P sub 2 was a formula that we have dealt with. So we clearly understand that P sub 1 is going to be 0.5 since 6 out of 12 are going to be defaults. P sub 2 again is going to be 0.5. 6 out of 12 is going to be non-defaults. So clearly 0.5 multiplied by 1 minus 0.5 plus P2 again is going to be 0.5 here. 1 minus P2, that is 1 minus 0.5, will result in 0.25 plus 0.25, which is going to be a value of 0.50, which I have mentioned here. Same is the case with the Gini impurity that you can calculate at subnode S2, because you have the same proportions for defaults as well as non-default percentages here. So P sub 1 again is going to be 0.5 and P sub 2 again is going to be 0.5 in this particular subnode S2. So we multiply these weights with the individual Gini impurities that we have calculated at subnode S1 as well as subnode S2. So the resultant calculation will be like 12 by 16 multiplied by 0.5 plus 4 by 16, which is a weight of subnode S2, multiplied by 0.50, which is nothing but the Gini impurity calculated at subnode S2. So this here is going to result in a value of 0.50, which is called as weighted Gini impurity for the overall feature split. So we have computed the weighted Gini impurity for the feature split determined by this particular variable called credit card here. Okay. So we conduct this similar exercise for other feature splits as well. But just by looking at this overall value, we clearly understand that this is a maximum possible value for Gini impurity as per the graph that we have already looked at. So the maximum possible value for Gini impurity is going to be 0.50, which is occurring at this peak. The corresponding x value, the corresponding probability value again is going to be 0.50, which is what we are observing here in both the cases. In both the cases, P sub 1 was 0.50 and the resultant Gini impurity at its individual subnodes again turned out to be 0.50. The overall weighted Gini impurity also resulted in a value of 0.50, which is maximal. So it's a clear-cut case that we can go about rejecting this feature split altogether. And further, we are also looking at evaluating this feature split of credit rating. Here we understand the weight. The weight here is going to be 11 observations in this subnode S1 divided by total 16 observations that we can find in root node. The weight associated with subnode S2 is going to be 5 divided by 16, 5 observations that are available in subnode S2 with respect to total 16 that are available in the root node. Let's also calculate the Gini impurity at individual subnodes here. So here we understand P sub 1 is going to be 0.27, P sub 2 is going to be 0.73. The probability that we are selecting a particular data point that belongs to non-default class is going to be 0.73. That belongs to a negative class is going to be 0.73. That's what I mean. P sub 1 in this subnode S2 is going to be 1 and P sub 2 is going to be 0 because there are none of the data points that belong to negative class label here, and hence the probability of it being a negative class label is going to be 0. So clearly we can calculate the Gini impurity by plugging in these values in this particular formula that we already have looked at. So for subnode S1, it's going to be 0.27 multiplied by 1 minus 0.27 plus 0.73 multiplied by 1 minus 0.73, which is going to give a value of 0.27 multiplied by 0.73 plus 0.73 multiplied by 0.27. The resultant value is going to be 0.39 like I have indicated here. So I multiply this weight with 0.39 that I have arrived at for this calculation. Similarly, when I compute the Gini impurity for subnode S2, it's going to result in a value of 0 because having a value of 1 for P1 multiplied by 1 minus 1 is going to result in 0 altogether. Plus, anyways, the probability of it being negative class level is 0. 0 multiplied by any value is going to turn out to be 0. So the resultant Gini impurity for subnode S2 is going to be 0. The second term is completely equivalent to 0. And hence we multiply this term 11 by 16 multiplied by 0.39 plus 0 is going to result in a value of 0.27. This weighted Gini impurity for the feature split credit rating is 0.27, which is clearly lesser than 0.50 that we have calculated in the previous exercise, right? So 0.50 was the resultant weighted Gini impurity for credit card feature split, which was maximal value. And whatever weighted Gini impurity that we have deduced for credit rating feature split 0.27 is way lesser than 0.50, and hence having credit rating feature split is better than having credit card feature split, is what we can perceive from the discussion that we had so far. Let's also try and evaluate it for income group as well. I'm leaving this as an exercise to you. Just don't look at the numbers that I have provided here, but rather try to do the math for yourselves and finally compare the numbers with what I have represented in this particular slide. Okay? It's going with the same approach again. Like we compute the weights for individual subnodes. So this is subnode S1, subnode S2, subnode S3. For subnode S1, the weight is going to be 8 by 16. Subnode S2, the weight is going to be 3 by 16. Subnode S3, it's going to be 5 by 16. So we compute individual Gini impurity for subnode S1, S2 and S3. We multiply those Gini impurities with the corresponding weights and finally look at adding all of these resultant multiplication terms in order to attain what could be the weighted Gini impurity for the overall feature split income group. So we clearly understand that 0.19 is far lesser than 0.27 that we have deduced earlier versus 0.50 for credit card. So clearly income group is a winner here. So income group is a right feature split that we can implement for the decision tree model that we are going to construct, because that is the one that's going to produce a lesser impurity score. So this is the one that's going to produce as homogeneous or as pure subnodes as possible out of the total feature splits that we have tried to evaluate. So we have evaluated 3 different feature splits here. We understand that the income group feature split produced a minimal impurity value, and hence we select income group feature split over other feature splits that we have evaluated. So this is how you look at computing Gini impurity at individual subnodes, computing the weight, multiply the weight with respect to the individual Gini impurities, add up all of those terms in order to compute what you call as weighted Gini impurity for the feature split. Compare the weighted Gini impurity that you have calculated for different feature splits that you have evaluated. Pick the feature split that's going to produce a minimum impurity value like what you are currently observing for income group. Okay. So this is all I wanted to discuss with you in this particular session. So in the next session, we are going to further look at other impurity functions like entropy and how entropy plays a role in determining what could be the right feature split. And we can expand this mechanism for any number of feature splits that can occur. So as you can remember, the depth of the decision trees that we have considered so far is limited to 1. So we need not restrict ourselves to have a depth of 1. You can further allow the decision tree to have multiple other subgroups. Like let us say this is a subnode S1. You can further look at splitting this subnode S1 into 2 or 3, 2 or more subgroups again. So this could be S11, this could be S12, this could be S13 again, depending on a different feature split. So this feature split again will be evaluated by the same process. So you consider all the variables that you are having in order to understand what could be the right variable that you can use for feature split and what could be the right value associated with those features, again in order to understand the right feature split that's going to produce as homogeneous subnodes as possible by using the weighted Gini impurity calculation that we have done so far. So that's not restricted only for this particular decision that we are making at root node. That is also applicable for selecting any of the feature splits at any of the decision nodes that you can have. So this again here is a leaf node, and this does not apply to the leaf node, but any of the decision nodes that you can have for a higher depth value can essentially consider this calculation and attain the right feature split hereafter. Okay, so that's all in this particular session, and thanks for watching.